Hello, we are the team The Falls in our segmentation, and this is SafeStride.
Hey, what happened? Why are you crying?
I fell down on the road and got injured.
Oh my god. How?
I was walking on the road and texting Lily and I did not see a big stone. I got crashed to it and fell down. My right ankle is also bleeding.
Oh. Distracted walking. Give me your phone. Take the phone. I have installed SafeStride app on your phone.
What is SafeStride app?
When you use your phone while walking or running on the road, SafeStride app will send you a notification to not to use your phone because it is dangerous.
Oh, but how does it do it?
SafeStride app uses accelerometer, gyroscope and sensors from your phone and predict the posture of the person with the position of the phone by employing complex machine learning algorithms. It tracks your location using GPS, and if you're using your phone while walking or running on the road, it will notify you to prevent accidents and getting mugged.
Wow, so no more injuries. SafeStride app.
Woman was seriously injured in New Jersey when she tripped over an open cellar door and then tumbled into the basement. The 67-year-old woman was looking at her cell phone when she flipped headfirst into the basement about 6 feet below. Fire crews rescued the woman and took her to the hospital.
So here we can see a couple of more cases of distracted walking, and we can see the danger it is being caused. So our solution is trying to target this and trying to make sure that users are prevented from such situations happening when they're walking on the roads with their phone out. So let's get into it. Yeah. So looking at the trend, as the number of smartphones increase every year, so does the accidents as well. So we can see over here from 2000 to 2011, the accidents are steadily increasing. This is a bad sign. And some of them are because of simple distracted pedestrians who are using the cell phones on the road. So our solution, which is SafeStride, tries to target that. So it is used to produce a very high accurate prediction of whether the user is in a probability of danger while walking on the road because of using a phone and being distracted. So based on a very low latency mechanism, we're able to return or warn the user saying that you're in a probability of having your phone mugged or there is a probability of having accident. So please keep your phone inside. And right now it is only for phones, but this is universal and can be scaled to wearables as well, and it is very low cost as well. So the architecture of the solution can be broadly divided into two parts. The first part is to train the machine learning model, and the second one is the operation of the solution itself. So let's get started with the first one. So we have Node-RED running on the phone, which is able to collect the data, which is right now the accelerometer, the gyroscope values, and the label of what exactly is the user doing. All of these are collected, and it is you collected into a S3 bucket where all the data points from various multiple devices are pulled into one single file. And this one single file contains around 3000 data points as of now. And those data points are pre-processed and then they are fed into multiple ML models. So the accuracy is tested based on 9 classifications. So there are 3 human motions, and each motion again has 3 poses. So like for example, walking has 3 poses again, holding, calling, and pocket. Likewise for still and running as well. So the accuracy is tested, and we are choosing the top 3 models with high accuracy. So we are looking at an accuracy of around 93%. The second system architecture is the one which we are using to deploy, and this is the one which we'll be using to operate. So instead of the labels right now, the GPS coordinates are passed, and the AWS Lambda collects these values, and it has the ML models which are deployed as SageMaker ML endpoints. So they are used for the prediction. So we have 3 ML models over here. So the 3 ML models are used to produce the best out of 2 out of 3 prediction. So if 2 of them at least, or maybe all 3 of them, are going to give a decision saying that, okay, there is a probability of danger, and along with the GPS matching, so the GPS coordinates are matched against a set database of roads around the University of Southern California. They have the priority of whether there are high probability of accidents which are going to be occurring or a low priority. They are manually input. So this database is used to match and it's able to see whether the user is on a road or not. So when both of these are combined, the decision to send a feedback and to raise a notification telling the user to keep inside his phone is made sure. Now, the priority is used to have two kinds of notification frequencies. If the user is in a high frequency road, the frequency of notifications will be higher. So you're going to get a lot more frequent notification on your phone saying to keep your phone inside. If it's a low frequency, then it is going to have a little bit of lesser amount of messages to the user given.
Hi. So let's start with the flows for the training and the testing phase. So first, for training, we needed a collection of data sets so that we could train our models. And the services that we use for AWS is basically AWS IoT Core, which acts as a gateway for the rest of the AWS IoT services. And after that, we are using Kinesis and S3 bucket and as well as a Lambda function. And so the flow is basically termux will be running Node-RED on a phone, and the Node-RED flow will basically invoke the sensor values. And after the sensor values are output on the STD out of the phone, it's sent to AWS IoT Core with the Amazon certificate and all the other private key and public keys, which are required to communicate with the rest of the services. So after the AWS IoT Core receives one data entry point, we can act it as a rule to send it to a Kinesis file host system. So Kinesis file host basically acts as a data buffer. So after a certain amount of time or a certain amount of memory is reached, it will then write all the data in one particular file in an S3 bucket. So in this way, we get, by default, we have kept 240 seconds. So every 240 seconds, we'll get a new file in one S3 bucket. So we want the file to be in one location. We don't want all the data sets to be in one location. So for that, we are using a Lambda function, which gets triggered whenever there's a new file being made in the source bucket. So basically first bucket. And as soon as we get a new file, what this Lambda function does is basically it appends all the new entry to the existing entry and appends it to one file. So this makes the process easier so that we have all the data set, all our data entry points in one particular file. So this is the flow that we use for the training phase, where we want all the data entries in one particular place. And after that, after we trained our models and everything, the flow for the real-time prediction, basically the whole operation, is as follows. So we're using the same termux on Node-RED, which invokes the sensor values and the GPS through the termux API on Node-RED. And after we get the values, we send it the same way we did in the previous case, that is through IoT Core with the required IoT Core certificates and everything. So once the data is received at AWS IoT Core, it then forwards it to an AWS Lambda function. The Lambda function then parses the values as features to predict the phone usage by invoking the ML models deployed on AWS SageMaker. So the Lambda function, within the Lambda function, once we get the predictions from the three models, the Lambda function chooses the best two out of the three. And this basically improves our accuracy even further. And after we get the prediction and after we do the GPS matching to assign priority alerts depending upon how busy the road is, we store all the results in one particular S3 bucket. And another flow basically invokes a get HTTP REST API request through AWS API gateway for feedback. So once that is invoked, a separate Lambda function is invoked, which basically accesses that S3 bucket, which has the result, and basically gives the values of whatever prediction and the priority has been set back to our phone. And depending upon how busy the road is, or whether the phone is safe, or whether the danger has been detected, the haptic feedback and the visual push notification will be triggered.
So first of all, we need to send census data to AWS. We are using accelerometer, gyroscope, and GPS sensor for project. So we are using Node-RED to collect the data from the smartphone. Here we can see this location tab. It is collecting GPS data from the smartphone, and this exact command will collect accelerometer and gyroscope data from the smartphone. We are converting the data into string stream for AWS IoT, and we are sending our data to AWS IoT core using HTTP request method, the post method, and using URL given by the AWS IoT core. We can see here we have received data in IoT core. The interval of data sending is 2 minutes. As soon as the data arrived at AWS IoT core, it will invoke a Lambda function, which will deploy the machine learning model for the prediction.
So this is the final data set that we use to train our models. And after shuffling and converting into CSV, this is how the data set looks like. So we used AWS SageMaker to train our models, and we used 3 different models. And after experimentation, we finalized on the ones that gave us the highest accuracy. So the 3 models that we chose were as follows. So one, we choose the physical activity and the phone pose as a combination of all the 3, so that we have in total 9 classified labels, and we use random forest for that, which gave us the highest prediction, that is 84%. Then another method that we use is to basically use random forest to just predict the physical activity of the user, and then append that prediction to the existing features, and then using random forest again to predict the phone orientation. That gave us an accuracy of 93%. And the third model that we decided on was use KNN to predict the physical activity, and use the same method that we did for the previous case, that is using random forest to predict phone pose, with the added feature of the previous prediction, which gave us a 91% of accuracy. So these are the 3 models that we finalized on, and these models were deployed on SageMaker as the endpoints, which can be invoked on, which can be invoked by a Lambda function. So this is the Python notebook that we use to basically deploy our SageMaker models, train and deploy. So you can see that we have decided on a role, and then we are giving access to write it on a basically on an S3 bucket. And we see that we are using ML model.py, and it's different for different models. So ML model.py is basically the the first case that I explained, basically the 9 classified models. So you can see that 0 is allocated as walking holding, 1 is walking pocket, and etc. So in this case, you can see that X-train features is being read as the first 6 columns, which are the first 6 features, and the Y trains are the labels that we use for a training phase. We standardize as we use standard scaler to standardize our data set, and then we are using the 9 classified labels, and we're using random forest. And the hyperparameter that we decided on, the tuned our model to, is 15. So this is mlmodel.py, and after we train it, we deploy the model, and you can see that we are getting an endpoint. So we do this thing for all the Python models that we decided on, ML models that we decided on. So mlmodel.py is the first case that I explained. Model 1 is the random forest to predict just the physical activity. So that's why you can see that it's only taking one particular label. Model 2 is basically using the predicted values from the first to predict the second. So that's why we are training based on the first one as an added feature. That's why you can see that I've appended the basically the 7th label to the feature, so that it can be added as a additional feature column. So, and model 3 is same as model 1, just to the case that the first case is KNN instead of a random forest. So after we have all these model.pys ready, we basically train our models and deploy them. And in that case, we get different endpoints, and then we use these endpoints, which can to basically for the lambda function to invoke these endpoints for the prediction. And in the prediction, we use best 2 out of 3, so which even for improves our accuracy.
The AWS IoT core then triggers the Lambda function, which uses the data and applies it to 3 machine learning models which are deployed. So the best 2 out of 3 approach is used to arrive at a final prediction. So the GPS coordinates are kept in a database which is stored in a keyhole markup language file. We'll look at it later. And afterwards, the GPS coordinates of the phone is compared with the database. And afterwards, it's found out to find out the priority of the location, whether if it's on a road and what is the priority. So based on the final prediction and the location of the phone, the decision is made to whether raise the feedback or just keep quiet. So now let's look at the AWS Lambda code. So this is the Lambda code. So over here we have done the necessary imports, and we have our endpoints declared over here. And this is the bucket names, and this is the KML file. So we'll get to the KML file shortly. And we are keeping the KML file and we are invoking a parser. So now this part is the function which is actually triggered. So over here we can see that we are getting all the data from all the sensors, and afterwards we are invoking the endpoints. So this is the first model, which is the combined 9 models approach, and this is the second model, which is the RF, which is the random forest, which is linked to another random forest. And this is the third approach, which is the KNN, which is linked to a random forest. So based on that, there are 3 predictions, and these 3 predictions are considered in a best 2 out of 3. So if any 2 of the 3 minimum tell a yes, then it's predicted to be true or predicted to be in danger. Otherwise, it's predicted not to be in danger. But one more thing, what we need to check is the GPS location of the phone. So for that, we have a KML file. So the KML file is used to access all the coordinates of couple of multiple roads with priorities which we have assigned. So we can look at the KML file over here. So for example, there's an example KML file of 2 roads. So this is Menlo Street and this is Orchard Avenue. So this is the start location and this is the stop location of Menlo. Similarly, start and stop of Orchard, and these are the priorities assigned. So this is automatic. This is compared manually, and it is checked to see if it's on any road. And if it is on any road, the priority is noted down, and all of these is returned into an S3 bucket.
Hello, I'll be explaining about the current operation of feedback mechanism. So to get started, we need to create a new Lambda function for the deployment of feedback mechanism. This Lambda function has full access to S3 bucket, where it will be reading outputs from a text file called as output.txt. Initially, the output.txt does not have any information in it, but as the first Lambda function finishes its job, it's going to upload the new data on output.txt, which should be read by the second Lambda function. So the outputs will be in the format of prediction and priority as sent by the first Lambda function to S3 bucket. And once there is information inside the S3 bucket's text file, that is the file size increases, that's when the second Lambda function is triggered. So the output has prediction and priority. Prediction can have 2 values. It's either 1 or 0. If prediction is 1, then the user is walking or running on the road using their smartphone. Then our application will trigger the notification asking user to keep the phone inside. If prediction is 0, then no notifications will be triggered. If the priority is 1, then the user is on a road which is heavily crowded and the number of reported accidents are high in that road, hence multiple triggers will be sent. If the priority is 2, then only one notification is sent. The outputs in the text file will be in the format of JSON string, and this is how the outputs are going to look like. We will take a look at them in our CloudWatch. Because we have printed our prediction response, we have this prediction as 1 and priority as 1 from our Lambda function. And now we need a mechanism that will convert this information into a notification on user's phone. So we used the combination of AWS API Gateway and Node-RED to achieve this. So the API Gateway will be in between our backend services and our client. And Amazon API Gateway is an AWS service that is used for creating, publishing, maintaining, and monitoring REST, HTTP, and WebSocket APIs at any scale. So we start by creating a new API with default permissions. And we will create a new resource. Let's name that resource test. And we'll be creating a new method called as get function. And here we are using this API gateway as a trigger to our Lambda function that we have it right here. So we need to enable proxy integration with Lambda, and we have to give the name of our Lambda function. So once that is done, we are ready to save our API gateway. This API gateway is configured to get results from our Lambda function that has our final output of our user. So here is the diagram of our API flow. The client sent a get request, which is passed through the Lambda integration. Then it was executed and it is passed back as a HTTP response back to the client. So let's deploy our API. We just need to create a new stage. And finally, our API is ready and deployed. We need to use this URL at get function on our Node-RED to access our final output and send notification to user. This will have our final output. And our final output is in the form of a JSON string. It's a prediction as 1 and priority as 1, as we saw before. This is our flow for our Node-RED feedback mechanism. In the same way as we had in our API gateway, we have HTTP request node with the get function as the method, and this URL is mentioned right here. The result is now converted to JSON and it is sent to our function where we are declaring two values that we got from API gateway. We have message.payload.prediction defined as prediction, and we have message.payload.priority defined as priority. This value is now returned to our main function, which decides whether to trigger the notification and vibration on the user's smartphone or not, or what's the priority of the notification. So we start by converting our prediction and priority to string. We have two simple if conditions. The first condition checks if the prediction is 1 and if the priority is 1. If it is, then the Node-RED sends a notification from our application SafeStride saying, "High accidents reported in this zone. Please keep your phone inside your pocket." And it's going to wait for 3 seconds. After that, it is again going to send a trigger notification because the priority is currently 1. If the priority is 2, then Node-RED will send just one notification saying, "Please keep your phone inside your pocket." And this is our priority 2. For any other case, no notification is returned as we are returning null here. Our trigger mechanism has a push notification with phone vibrating. This Node-RED flow is currently running on the Termux that is installed on user's smartphone. So once the data is sent from API gateway, it'll be accessed at HTTP request, and the final output is going to look like this. This is the notification sent when user is in priority zone 2 and user is using their phone on road. Let us see another example where user is in high priority roads. This is how the notifications are triggered on a user's smartphone. Now let us take a look at how these notifications are seen on smartphone. We got this notification twice because our prediction is 1 and our priority is 1. So that's why it's reporting high accidents in this zone and it's asking to keep the phone inside. Let's take another example where the user is located in a low priority or a normal road. So in this example, we only get one notification saying, please keep your phone inside your pocket because this is in priority 2 zone. That was another look at how multiple notifications are sent by Node-RED because of the prediction and priority set.
Okay, for cost analysis, we are using AWS IoT Core, Kinesis, Lambda, S3 bucket, and a SageMaker in our project. As you can see, that AWS IoT Core is free for 12 months, but after that, we are only sending 21,900 messages per month. So after 12 months, will be cost $0.0219 per month. The price of Kinesis is nil, and for the lambda function we are only sending 43,800 requests per month, so its cost is also nil. And for the S3 bucket we are not using that much storage for our solution, so its charge is 0. And for the SageMaker it is free for 2 months for instance m5.xlarge. So after 2 months, as we are using m5.xlarge instance, it will be cost 0.269 per hour. So as the users will increase, the cost will increase linearly due to scaling. So here is the summary of our solution or final project. So in the progress 1, we have collected the data set for 9 labels, multi-label and multi-class, and we have completed data set processing. In the second phase, we have tried and employed various machine learning algorithms and decided to move forward with the best 3 according to the accuracy of the models or for our multi-level multi-class data set. And in the final progress, we have deployed ML algorithms on SageMaker and created endpoints. We have also created a feedback mechanism to send the prediction to the users on its mobile with the vibration and notification. And we have tested our prototype and it is working perfectly. So here I conclude this project of EE542. This project can be applied on a big scale to help the society and the safety of the people for the pedestrian distracted walking. These are the references which we have used for our project, various articles, research papers, and the statistics. Thank you.